Hello and welcome to this presentation. As you've heard, my name is Gustav Steinberg and I'm a technical promoter for high voltage protection. Today, I will show you how you can efficiently implement accurate switching, closing and opening with SIPUTEC 5 to practically eliminate transients. The function to achieve this is a point-on-wave switching application in SIPUTEC 5. So, now let's have a look at what is required to do a point-on-wave switching application with SIPUTEC 5. The presentation will be in 3 chapters and we will conclude with a brief summary. Chapter 1 provides some general information on the equipment required. The SIPUTEC 5 device selection is also covered. Chapter 2 shows how the configuration with DIXI is done, highlighting the method of operation and the calculation of setting parameters. Chapter 3 summarizes the methods applied during commissioning to check the correct operation and the adaptation, fine-tuning of the settings. So, let's then start with Chapter 1. The device selection and configuration as well as hardware requirements. To begin, where is point-on-wave switching a benefit? As shown here, a capacitive load or cap bank was energized. On the left side, the instant of closing was at voltage peak and severe voltage transients are seen. These transients have the potential to severely damage plant and equipment, including the energized capacitor. On the right-hand side, the same capacitor was energized correctly with point-on-wave switching, close to the zero crossing of the voltage. There are almost no induced transients due to the closure. So the advantage of point-on-wave function or point-on-wave closing function is very clearly demonstrated in these diagrams. Where can point-on-wave switching be used? Is it only on capacitor banks as shown on previous slide? And the answer is no. Point-on-wave switching can be used almost always, as transients are generated by every closure and opening of circuit breakers. The situations that are listed here are of particular interest. Inductive loads, such as transformers and reactors, typically have iron cores. When these iron cores saturate during closure, as shown on the left, there will be a severe inrush current during saturation. If the inductive load is closed by point-on-wave, as shown on the right-hand side, the flux dashed line will have no offset and will therefore have no inrush current as it does not go into saturation. Point-on-wave switching, closing and opening is therefore of particular interest for the cases listed here. Inductive loads, transformers and reactors, capacitive loads, capacitor banks, and to a lesser degree, transmission lines and cable feeders. To get started, you need to note your application: transformer, capacitor, or something else. Is the capacitor grounded or with isolated start point? Then you must decide if the application will be for closing, opening, or for both. The point-on-wave function in SIPUTEC 5 is prepared for all of these applications. The circuit breaker is a very important central component of the point-on-wave application. For the intended application, for example point-on-wave closing, the circuit breaker must have phase-selective closed coils to enable each phase to be closed independently. This is shown in the diagram where for each pole, A, B and C, there is a separate closing contact in the IO209 at the top. as well as a separate trip contact for each pole in the IO209 in the middle. This phase selective connection of the closing and or trip contacts is a must for the point-on-wave application. The mechanical circuit breaker position during switching can be obtained with standard auxiliary contacts via binary inputs. If the breaker has a reference contact with more accurate switching position status, this can also be implemented via transducer input on IO212 module. It will be shown later how this information is used during commissioning to check and adjust the function. The circuit breaker response time is of central importance to the point-on-wave function. If conditions such as ambient temperature, hydraulic pressure or control voltage have an impact on the response time, this may be compensated in the point-on-wave function. For this purpose, these conditions can be monitored via transducer inputs, as shown at the bottom of the diagram. Part of the determined scope of the application is, will point-on-wave be for closing and tripping or only for closing or tripping? Depending on the load, inductance, transformer or reactor, or capacitance, the load side measurement for monitoring the point-on-wave must be applied. With transformers, for example, a voltage measurement on the load side is used to monitor the closing. This is done because the current, only the magnetizing current, is too small to be used as a dependable criteria during point-on-wave closing. For capacitor loads on the other side, either current or voltage may be used. Here, the current is fairly constant and equal to full load current after energization. This monitoring current and or voltage is the transformer shown at the bottom of the diagram. The reference voltage used prior to switching by the point-on-wave function is on the source side of the circuit breaker. In the diagram, it is a voltage transformer at the top connected to the bus bar. This voltage transformer must be available. In applications with multiple bus bars and correspondingly multiple bus bar side voltage transformers, it is possible to connect all of them to the device and implement an internal selection logic depending on the switching state of the bus bar isolators. It must be checked if the circuit breaker mechanical switching will be monitored with reference contact and transducer inputs, so-called Hall effect sensors, in the middle of the diagram, or alternatively via auxiliary contacts connected to binary inputs. Finally, the use or not of sensors for temperature, control voltage and hydraulic pressure must be defined. All of these decisions regarding the scope of supply are finalized. The device may then be selected as shown in the next slide. The hardware configuration of the device may now be done. For the point-on-wave function, the following must be considered. Voltage and current measuring inputs for the reference voltage as well as load side current and or voltage. High-speed contacts in IO209 modules for point-on-wave switching commands. All switching commands by point-on-wave must be via such a high-speed contact in the IO209 module. Transducer inputs. If a reference contact is used in the circuit breaker, it must be connected to a transducer input on the IO212 module. Fast transducer inputs. The other optional inputs for temperature, voltage and hydraulic pressure may also be connected via the IO212. Alternatively, these not time-critical signals can be connected to a plug-in transducer card as shown in slot F. Other CPROTEC 5 features may be selected as desired. This concludes Chapter 1, Device Selection and Configuration. We will now proceed with Chapter 2, Dixie Settings. An outline of the settings required for a point-on-wave application will be covered, including some example setting calculations. The point-on-wave function is implemented in the function group circuit breaker with single pole, trip and close capability. It is therefore restricted to the device types listed at the bottom: 6MD86, 7UM85, 7SA87, 7SD87 and so on. The close and/or trip commands issued via the control function of this circuit breaker will be the point-on-wave switching operations. In this manner, the point-on-wave function is fully integrated into the standard control logic of CPUTEC 5, e.g. close command via IEC 61850. The point-on-wave interface with measuring inputs, left-hand side of diagram, and binary inputs and outputs, right-hand side of diagram, is configured in the normal manner and will be covered in more detail in the following slides. Following the standard practice in Dixie 5, the point-on-wave function can be found in the global library on the right-hand side under function group circuit breaker single pole. With a mouse, it can be dragged and dropped into the desired function group circuit breaker in the project tree on the left-hand side, as shown in the diagram. Once this is done, the further setting steps in Dixie can then be done. The current and voltage routing, the standard CPUTEC 5 procedure is to make the interface to measuring points at the function group level, so that all functions within the function group have access to these measured values. For the point-on-wave function, the reference voltage at the top is the VSync 1 voltage. The corresponding X must be applied as shown, so that the bus side voltage is routed to VSync 1. The load side current for monitoring and/or voltage are the normal current and voltage measuring points of the function group circuit breaker. These are also selected with X in the corresponding position as shown in the left side. Selecting the application: capacitive load, transmission lines, reactance, transformers, or user-defined. Depending on the selected application, here a capacitive load with isolated star point is selected. The recommended switching angles are automatically proposed as shown. Note, the closing angle is always defined using phase A of the reference voltage. These settings therefore refer to phase A of the reference voltage. For the capacitive load with isolated star point, the closing is best at 30 degrees for the first poles A and C. At this point, the voltage VAC is 0. This is shown in the encircled settings. The pole B closes a short time later at 120 degrees. Remember, 120 degrees on phase A. At this point in time, the phase B voltage has a 0 crossing. The method behind this will be shown in more detail on the next slide. The settings are recommended, but the user may modify them if necessary. We will also show that later on. If we start at the bottom, we see the closing instance for a capacitor bank with isolated star point, as said on previous slide. With the first switching in phase A and C at 30 degrees. At 30 degrees on phase A voltage, the A and C voltage intersects so that the voltage VCA has a 0 crossing. Closing poles A and C here will be ideal as the start point is not grounded and there is no delta between the load side. Discharge capacitor equals 0 volts and the in-feed also 0 volt at this point in time. The grounded capacitor at the top is different. Here the phase A will be first to close at the zero crossing of the A phase reference voltage. For the grounded capacitor this is correct because the A phase capacitance to ground will have 0 volt before closing. The other poles at the top close in succession at their corresponding zero crossings. Note how the arrows point to the instance of closing each pole and how the angle setting corresponds to the phase A reference voltage. The circuit breaker is, as was mentioned earlier, a key player in the point-on-wave switching. The diagram here, extracted from the point-on-wave manual, is for the key parameters used in the point-on-wave closing. A similar diagram is also available for point-on-wave opening. The closing time, highlighted in the bar in the middle of the diagram, is the first value that must be set. It can be obtained from the circuit breaker data and is set for each phase as shown. It is the time from initiating the close command by IO209 contact on left of diagram until the primary contacts of the circuit breaker make first mechanical contact. Important, all the other timing values will be calculated starting with this setting. The equation that calculates T close phase A, shown directly below the CB closing time bar in the diagram, indicates this. Based on the set closing time as done in the CB data settings, the actual closing time is calculated as shown in the equation by considering the influence on closing time, transducer inputs, as well as the set correction time. This correction time setting is the key parameter for adjustment during commissioning, as will be shown in Chapter 3. Initially, the correction time would be 0. Now, the make time. The make time is shorter than the closing time because it ends when current starts to flow, equals electrical contact. The definition of make time is simple, as shown in the second equation. It is the closing time minus the pre-arc time. The make time is used by the point-on-wave function to determine the instant of closing as set with the reference voltage angles. So, when analyzing, it is important to remember closing time is the starting point of all calculations. The measured closing time is with reference contact or auxiliary contact. The make time is relevant for timing of the output contacts. The make time is measured with current or voltage on the load side after closing. This will be shown again in Chapter 3, Commissioning and Adjustment. If compensation, this is optional, if compensation of the closing time due to ambient temperature is required, this can be implemented with a temperature sensor connected to a transducer input. Configuration of the temperature compensation is as shown by selection of the corresponding transducer top left diagram. A linear, or as in this case user-defined compensation, can be selected as shown in the bottom diagram. For the user-defined compensation, setting points from the curve on the right-hand side can be entered. Note that the curve shows two influences on closing time: temperature and control voltage. In this case, control voltage has a linear influence between 85 and 100% of nominal voltage. This will be considered separately in the following slide. For the temperature compensation, it is assumed to be at nominal voltage. over the indicated horizontal temperature range from minus 40 degrees C to plus 40 degrees C. So here in this slide, it is shown how the control voltage compensation is done. Select the corresponding transducer in top left diagram as before. Apply a linear characteristic in this case. The slope setting of the linear characteristic is calculated with the shown equation. The slope equals the delta time difference between extreme 85% closing and nominal voltage closing time divided by the voltage difference. It is best to do this at normal ambient temperature, e.g. 20 degrees C. In this case, the delta closing time is approximately 77 milliseconds minus 72 milliseconds equals 5 milliseconds as shown in the diagram. The voltage difference is minus 15% of nominal closing voltage, for example, 220 volts DC. The equation returns a slope of minus 0.16 milliseconds per volt in this example, which can be then set as shown in the bottom of the diagram on the left. The transducer inputs for compensation described in the previous slide is configured in the normal manner. Set the scaling parameters according to the transducer rating and be sure to select current or voltage as input signal depending on the nature of the transducer signal. A final aspect before we go to chapter 3 is the rate of decay of dielectric strength, simply called RDDS. As will be shown here and again in chapter 3, this can be of importance for some applications, especially for capacitor load closing. What is RDDS? It is a value we can use to determine the pre-arc time. In the diagram, the red and blue curves, S1 and S2, are RDDS curves for two switching times, two instances of closing. The two switching times are only a short distance apart, less than half a millisecond, as can be seen where they intersect the x-axis at 15 milliseconds, respectively 14.6 milliseconds, so 0.4 milliseconds apart. At this point, where they intersect the x-axis, the breaker primary contacts make first mechanical contact, as shown from earlier. This is the end point of the closing time. On the vertical axis, voltage is the indicated value. At the start of the close process, the contacts are far apart and the RDDS is very large. As shown by S1 and S2 curves, they are off the scale. As the separation of the contacts decreases, the RDDS voltage values decrease until it is zero when the separation is also zero. Pre-arc will occur when voltage across the contacts exceeds the RDDS curves. With the early closing, red S1 curve, the voltage exceeds the RDDS at 11.5 milliseconds. At this point, electrical contact is made. There's a breakdown and arc comes and current starts flowing. The make time end is determined here. The pre-arc in this case is from 14.6 milliseconds, the intersection or mechanical contact of S1 curve, where X1 intersects the x-axis, end of the closing time in other words, and to 11.5 milliseconds where current flow started. That is 3.1 milliseconds pre-arc time. For the slightly later S2 closing, less than half a millisecond later, we said 0.4 milliseconds later, the voltage never really exceeds the RDDS, so that the make time almost equals the mechanical contact, closing time in this case. Therefore, although S2 close was only issued less than half a millisecond after S1 closure, the current flow in S1 close was 3.5 milliseconds later, than S2. For point-on-wave closing near zero voltage, as in capacitor loads, this can be a problem. To compensate for this problem, the target switching instant can be moved to slightly after the zero crossing, so that instead of using S1, which is near zero crossing, move the target to S2, which is 0.4 milliseconds later. The equation shown here how the 0.4 milliseconds later target is converted to an angle of 7.2 degrees at 50 Hz. By increasing the set closing angles accordingly, the target closing is shifted to S2, which can prevent the much too early closing of S1. So, in the final chapter now, procedures applied during commissioning are covered. These are done to check if the settings are correct, as well as to optimize the point-on-wave switching by setting correction times that make allowance for the deviation of the circuit breaker timing from reference values. To start off, we identify what the point-on-wave function is doing during its closed cycle. First, it calculates the closing time based on the settings and the transducer inputs. This is the top equation. Sorry, I'm a little bit late. This closing time includes all influences and is the defining value for point-on-wave closing. Next is calculated the make time with the set pre-arc time and the above calculated closing time. This is the second equation. It is shown in the right-hand side diagram and will be the time from issue of close command until electrical contact, in other words, current flow. I think I went one slide too far, sorry. The calculated make time from the second equation and the set point on the wave point-on-wave reference voltage angle are used to determine the actual instant for closing the contact. See diagram at the bottom. In the diagram at the bottom, we see the set point-on-wave angle, e.g. 30 degrees. We then move to the left with a calculated make time and establish the instant in time for the point-on-wave close command. In other words, where the contact in the IR209 will close. All these times are listed by the point-on-wave in the fault log as shown in the next slide. After the point-on-wave close, read out the fault log as shown. The calculated close time for each phase is shown. This is the calculation as per the shown equation. For example, the calculated close time for phase A is 80.700 milliseconds. The next entry in the fault log that we check is the measured closing time. For example, 79.025 milliseconds for phase A. This is a time measured by the reference contact or auxiliary contact. A delta value is also indicated for the closing time, e.g. minus 1.675 milliseconds for phase A. This is simply the difference between measured and calculated closing time. The assumption is that the calculated closing time as per circuit breaker data is correct. The deviation of the measured closing time is due to offset of the reference contact or auxiliary contact. This offset can be compensated by changing the reference contact time delay as shown in the settings at the bottom right-hand side. Note, this reference contact time delay does not affect the calculated closing time. See equation at the top. The next value from the fault log that we check are the make time values. The first one is the calculated make time. For example, 79.8 milliseconds for phase A. This is calculated with the shown equation. Calculated closing time minus set pre-arc time. The next very important value is the measured make time. For for example 79.975 milliseconds for phase A. This was measured by the point-on-wave function with a current on the load side as shown in the diagram on the right-hand side. From the initiation of the close command, binary trace at the bottom is not matched in the time scale until current flow in phase A, that's the blue cursor in the diagram, the make time is measured. The calculated value was 79.8 milliseconds. That's the blue cursor at 30 degrees on reference voltage. Calculated. The measured value was 79.975 milliseconds or 0.175 milliseconds later. On the scaling in SIGGRAPH, this small time difference cannot be shown, but it is apparent that the function was close to perfect, only very small deviation. The make time can be adapted to compensate for the observed delta. This is done with the correction time as shown in the settings at the bottom right-hand side. A positive delta make time indicates that the close was too late. Here, 0.175 milliseconds too late. If the make instant is too late, the close was issued too late. This means that the calculated closing time was too short. It must be increased by the delta make time of 0.175 milliseconds. As the correction factor has a negative sign in the equation, a negative setting must be applied to obtain a longer calculated closing time. In this example, set the correction time for phase A to minus 0.17 milliseconds in order to increase the calculated closing time by this 0.17 milliseconds as shown in the blue values. The increased calculated closing time will automatically increase calculated make time, so that the next close with these settings will be issued 0.17 milliseconds earlier. This is the only parameter that should be changed to compensate for observed delta make times during service. For near zero voltage capacitor bank closing, it may be necessary to check the RDDS curves. The circuit breaker will not always close with exactly the predicted speed, even if all influencing factors are considered. There will be some scatter in the operating times. In this diagram, it is shown that the extremities of the scatter will result in make time termination electrical contact at point A earliest and point B latest. For a capacitor, point B is okay, close to zero, but point A is bad as it is at 70% of peak voltage. This can be improved as shown on the next slide. If the target is moved slightly after the zero crossing, the scatter will have a smaller influence. The earliest point A will ideally have the same voltage level as the later point B, the latest point B in other words, and will be significantly smaller than the original A point shown in gray. Here the optimal switching point was shifted by the adjustment time and the maximum voltage was reduced to 37% of peak voltage. Remember, it was 70% before the adjustment time is applied. When the target is at the voltage peak, this would be the case on transformers and reactors, the RDDS has a smaller influence, as shown in the diagram. The scattering will not move the voltage significantly away from the target of 100%. No adjustment is typically required in these applications. This brings us to the end, at which point I would like to summarize with the following single slide. The point-on-wave function in CPUTEC 5 has the following advantages. The user profits from the proven and standardized hardware of CPUTEC 5 as well as the system features, for example, communication protocols, cybersecurity, and so on. The point-on-wave function can be combined with other functions in the same device, for example, a bay controller or transformer protection. All the standard point-on-wave functions and features for closing and opening are included. Detailed process data, fault log, as shown earlier, is provided for clear and defined analysis and adaptation during commissioning and service. This ensures a quality experience over the entire life cycle. Thank you for your investing your time in my presentation.
Thank you, Gustav, for spending time with us and presenting this interesting stuff around point-on-wave switching. I once again learned a lot, and I will take care of memorizing that. And we have a lot of questions from the auditorium. I think the first one that came in is probably not really your topic here, because AC would like to know how MindSphere IoT Cloud Edge Computing deployment is leveraging power and utilities. But that's a perfect question for tomorrow around 12 o'clock. There we talk about the value of data and how with IoT solutions you can benefit. So join us tomorrow in the session with Bruno Opitsch. But now I have a question for you, Gustav. Okay. In case of generating unit, can I use point-on-wave switching even there is a 25 IED?
For generators, typically they need to be synchronized to the power system, because a generating unit would not be switched with a point-on-wave function. You have to switch it with basically a synchronizing device to get it synchronous to the power system.
Sure, yeah. I mean, they both have to run on 50 hertz and the same frequency, and otherwise we'll have a problem in the network.
So the point-on-wave switching there is actually automatic by the synchronizing device.
Okay, yeah. Next question is, how many circuit breakers can control one point-on-wave IED?
So you can put the point-on-wave function into each circuit breaker, and remember in CPUTEC 5, for each breaker we would have a separate function group circuit breaker. So if you have multiple function group circuit breaker in your device, you can apply the point-on-wave in each one of those, assuming that you have enough inputs, because you obviously have to measure the inputs, the binary inputs and the reference contacts, and also the voltage or current from the load side on each breaker.
Okay, so might be...
It's just the size. It's just a size issue, okay. How big you make the device and how many connections you can have to it. So each circuit breaker you can implement can have its own point-on-wave function.
Okay, thanks. And another question is, how would the point-on-wave act when you need to have a quick shut-off if there's a fault, such as electrical fire trip?
This is a very good question. I should maybe have put it in the presentation. The point-on-wave switching is typically organized by control. If you're doing a control switch, so basically a protection trips are not switched with point-on-wave. They go instantaneous to switch off the fault condition. Whereas you can, on the other hand, maybe do an auto reclosure you could have done with point-on-wave, or a control. You can do controlled opening and closing can be with point-on-wave. But protection functions don't operate the breaker with point-on-wave. They go directly, instantaneously. You can also set in the point-on-wave if it is critical. In some cases it's so critical that you could maybe energize a capacitor only with point-on-wave, so a close without point-on-wave is not possible. So if the reference voltage is not there, you cannot close. You'd have to organize a bypass, or you can set that it's optional, that if the point-on-wave is not available, you do a normal close, but if the point-on-wave is available, you use a point-on-wave function.
Okay. So I think in the regular switching, it's like protecting the device, and if we have a fault in the network, it's protecting all devices behind and just switch it off.
So a fault is just as fast as possible and no waiting for the point-on-wave. But if you're doing a controlled, no fault, then it can be with point-on-wave.
Yeah. Thanks. And the next question is something where I'll take the answer. Will this presentation be available for download on some online platform? Yes, this whole presentation has been recorded and it will be available for you to download. with all the information that Gustav gave with it. And the next question. The mechanical error of the circuit breaker could diminish the advantages introduced by the point-on-wave method. Could you please underline what circuit breaker characteristics were considered in the circuit breaker standard when implemented this method?
Yeah, it's obviously, as I said, the circuit breaker is a central component of point-on-wave switching. And we must remember that the timing, you saw the timing, if we were 2 or so 3 milliseconds off, it was really critical. The point-on-wave was really lost its efficiency. So the circuit breaker timing is critical. And as we know, circuit breakers will have a fairly predictable operator response time. And that's why the commissioning procedure is very important, that you, during commissioning, check this, because even if the circuit breaker manufacturer will have his data sheet, and you'll get a closing time of the data sheet, and you will then set that and do the first cycle, and you would see from the response time, is it dependable or not? And those commissioning steps will show you if it is working or not. And you should also check, obviously, the data. The circuit breaker manufacturer can say, right, I have a breaker with a very predictable response, and we would then tell you there's a temperature dependency, in which case we have to use a temperature transducers to compensate for those influences. And I think if we use a lot of compensation like temperature, hydraulic pressure and voltage and all of these to compensate timing, which we can do, then you can get a very good response from most breakers.
Thank you, Gustav. I see some more questions in the line. We are a little bit not really running out of time. Gustav, we are the last presentation for today. Do you spend some 5 or 10 minutes more with me?
I can do that. Yeah.
Thanks. So we continue the question and answer round for some more minutes. And feel free to stay with us, or, well, yes, just stay with us. No, you're free to leave too. So we go for the next question. When there are pre-insertion resistances, are they declared to the CPROTEC relay?
Pre-insertion, that would be in the breaker, because if you have stacked breakers, then you would have some resistances to basically spread the voltage, that the breakers don't close in a staggered way, one after the other. That is a breaker functionality. I think that is not considered in the point-on-wave. That would be an overall breaker response issue. This is not relevant to the point-on-wave.
Oh, okay, thanks. And in the future, point-on-wave, is it possible to learning environment system by itself and then decide to close or opening by automatically?
This, I think the question is the automatic adaptation, looking at the history, because obviously the point-on-wave function can register its past cycles, and so it will know from what it has done previously what the breaker response was. We're always coming back to the breaker and learn this. This is a feature that is still on our roadmap under development and will be available. So the point-on-wave function would then remember the last 3 closures or more were like this, and then would predict that the next closure would be. So it can, that adaptation time, that correction time, I said, would be an internal automatic feature in there as well, based on history.
Cool, sounds interesting.
But that's the future function.
Stay tuned. And then, can you tell us a little bit about how the point-on-wave function is implemented? Like just a general idea.
Well, it's a question, because it is now available in CPROTEC 5, one is finding more application. In the past, it was a function, the PSD was a Siemens product, very closely related to circuit breakers. So when you had an application where you identified right from the beginning, I'm going to use point-on-wave, you went to the circuit breaker manufacturer and said, I need point-on-wave from the circuit breaker, and they put a special box next to the circuit breaker to do this. So it was, remember, this close relationship by point-on-wave function and circuit breaker is there, but it was a more long-term decision. Nowadays, you can, as I showed, all closures have transients, so we can use it more widely. You can not only use it on those very special applications, like I showed on the capacitors, or on transformers, you can, on a transformer, effectively eliminate the inrush, as I showed. And in the past, it was not done very often, although you could maybe have a really big transformer. You said, okay, I'm going to use this point-on-wave device there. Now it is a function in CPROTEC 5, and you have more flexibility to where you apply it.
Cool, great. And can we get source side voltage through IC61850 for point-on-wave, or would that cause delays?
At the moment, that is not yet implemented. We'll have to wait and see if that option will be available. You are quite right that it's a timing issue, and that feature will hopefully become available.
Okay. And we take one last question. Do you have any reference of a system when you applied POW systems that results in a later enhancement or isolation coordination outcome?
Yeah, I think this is, first of all, point-on-wave references. There are some that we have, obviously. I don't want to list them now here. Not that many. The function has not been available that long. But then to now go a step further and say that what its influence was on the insulation coordination. Remember we spoke about the transient voltages. This is a design aspect, obviously, because in your insulation coordination you'd have surge arresters and so on to prevent transient overvoltage from absorb them and prevent damage. And I think in your insulation coordination you could consider point-on-wave switching and then say my transients will be lower, and then it would be a consideration to then, in the construction of your primary plant, use a different insulation coordination. In other words, save money on that side. But that is for the high voltage people, not for. We only provide the function to do the point-on-wave. How they are going to implement this in their system design or the high voltage plant installation, which is a money aspect, obviously, that you'd have to check with them. But definitely the point-on-wave can reduce transients and therefore could save money on the installation coordination.
Thank you. I think that was the last question in my row right here. Thanking you again, Gustav. Thanks for being here.
Bye-bye.
Thanks for my team in the background. They're doing some wonderful work there. You out there, have a nice evening here in the European zone, or have a nice rest of the day if you joined us from the Americas. I think the Asian colleagues are probably almost fallen asleep. I will meet you tomorrow morning again. So I hope to see you tomorrow. Have a nice rest of the day and take care and goodbye.